Welcome. Welcome to Silicon Photomultiplier Theory and Practice, a webinar presented by Hamamatsu Corporation and hosted by Photonics Media. My name is Robin Riley, and I am the web editor at Photonics Media. Our speaker today is Slawomir Piatek, a senior university lecturer of physics at New Jersey Institute of Technology and a science consultant at Hamamatsu Corporation. Hamamatsu Corporation is the North American subsidiary of Hamamatsu Photonics, a leading manufacturer of low-light photodetectors, including a wide variety of silicon photomultipliers. Before we begin, a couple of quick technical notes. If you have any problems, the easiest thing to do is to log out and log back in to rejoin the webinar. A recording will be available later today on our website if you miss any part of this presentation. We encourage you to ask questions throughout this webinar. Just type your question in the question box. We will have experts available to provide written responses throughout the session. Before we begin, we'd like to ask attendees two brief questions and hear your response. First question. Before today's webinar, were you aware that Hamamatsu makes and sells silicon photomultipliers or multi-pixel photon counters? Okay. And I see that many of you responded yes. And I'm going to close this poll now and share it. And I'm going to then move on to the next poll. And the second polling question is, what is the most important parameter or characteristic that a silicon photomultiplier needs to have for your application? Sensitivity, spectral response, speed, detector noise, operating voltage. Okay, thank you very much. I'm going to go ahead and close the poll and share the results. And I'm going to end the poll, and I am going to turn the control over to our presenter, Slawomir Piatek. Welcome, Slawomir.
Welcome, Robin. Thank you very much for the introduction. Let me just start the PowerPoint presentation. Robin, can you see my presentation? Can everybody see the presentation?
Yes, I can see it.
Thank you very much. Thank you, Robin, for a very nice introduction. First of all, I would like to welcome everybody. Good morning, good afternoon, and good evening, depending where you are, where you live. My name is Slawomir Piatek, and we're going to spend around the next 60 minutes discussing a very new addition to a family of photodetectors, a silicon photomultiplier, an exciting new device. So what is so exciting, what is so special about silicon photomultiplier? This slide may help us answer the question. It shows the detectability range of 4 photodetectors as a function of photon irradiance. Detectors are photomultiplier tube, an old vacuum technology, almost 100 years old as a matter of fact. A photodiode, a technology from about 60s, 70s, avalanche photodiode, and our new device, silicon photomultiplier. When photon irradiance is large, we can see that several photodetectors can detect light. When we have plenty of light, there's usually no problem in photon detection. However, when the light irradiance decreases, when we go to the level of few hundred photons per millimeter squared per second, the detection becomes difficult. And prior to 1990s, but more realistically prior to about 10 years ago, only photomultiplier tube was able to make detection at such very low irradiance level. The addition of SiPM gives now a choice, an opportunity to use a different detector than PMT at the irradiance level of about few hundred photons per millimeter squared per second. Thus, again, since about 10 years or so, we have a choice of detector at this very important range. How can SiPM detect such low light levels? And the answer is, it's the gain, internal gain of the photodetector. Please note that the internal gain does not increase the signal to noise of light that comes in. However, what it does, it makes noise, the effect of noise, added by front-end electronics, which is always necessary. A photodetector without front-end electronics is useless. We have to have some system to detect the current pulses that come from the photodetector. That front electronics introduces noise, and that noise is minimized or reduced by the internal gain of the photodetector. A quick comparison table between the four photodetectors from the slide one. Of course, the most important columns are the last two, where we compare silicon photomultiplier as an alternative, perhaps, choice to a PMT. I underscored a few advantages or maybe strengths of silicon photomultiplier. It's very high internal gain, in fact, comparable to that of the PMT. It's very low operating voltage, which is on the order of only a few tenths of volts versus 1,000 or so for PMT. SiPMs are immune to magnetic field, and they are very fast. In fact, almost as fast as PMTs. Our webinar is organized as follows. First, I'm going to introduce the product, discuss its structure. We'll spend quite a bit of time discussing its operation. This will be followed by discussion of some major opto-electronic characteristics of this device. We'll briefly discuss the modes of operation, 3 examples applications, and we're of course going to end with a mandatory summary and conclusions. One should think about this webinar as an introduction to this very new, very exciting technology. Silicon photomultiplier is a pixelated device. It consists of pixels, but I rather call them microcells, not to confuse the fact that SiPM is not an imaging device. SiPM is not like a CCD. It does not capture images. It's a point detector. The number of microcells ranges from several hundred to several tens of thousands. The size of microcells, or the pitch, ranges between 1025 to 100 microns. The active area ranges from about 1 by 1 millimeter to about 6 by 6 millimeters squared. All the microcells in SiPM are connected in parallel. Thus, SiPM has 2 prongs. One is called anode, and the other one is called cathode. In fact, electrical signal symbol of SiPM is the same as that for a diode. Because it's rather a new device, there are several names used to refer to this photodetector. The top 2, silicon photomultiplier, which I'm going to use, and MPPC, multi-pixel photon counter, are the most common. This information about the names is very handy when one makes a library or literature search on the device. Here we see a sample of offerings by Hamamatsu, a company that I represent. We can see that SiPMs come in various packages. Metal can, in this case, the SiPM also has thermoelectric cooling. A ceramic package, a surface mount, another surface mount, but four-side buttable, which is very good geometry to make arrays. Let's now discuss structure of a SiPM. We'll begin by looking at the single microcell, which is delineated by this green square on the left-hand side. We see this top of a microcell. A light would come and hit the microcell as we are viewing it. This squiggly structure on the top of the surface is a quenching resistor, and below insulating surface is avalanche photodiode. Thus, a single microcell of a silicon photomultiplier is a series combination of avalanche photodiode, which, as we'll discuss shortly, operates in Geiger mode, and quenching resistor RQ. All the microcells are connected in parallel. The quenching resistor is typically made of highly doped silicon, polysilicon, or metal. As I stated shortly before, light comes from above. Therefore, not the entire area of the pixel is photosensitive, because the resistor is certainly going to block some fraction of the incoming light. The fraction of the pixel or microcell that is actually sensitive to light is known as fill factor. Let's now look at the vertical cross-section of a single microcell. As stated before, on the surface we have a quenching resistor, which is connected through silicon oxide, through insulator layer to NP or PN structure below, which is the structure for avalanche photodiode. The actual structure depicted in the slide is known as N on P. So N-type semiconductor silicon on top of P-type substrate. The other version is also possible, which we'll refer to as P on N. As stated before, every microcell consists of avalanche photodiode that operates in Geiger mode. Let's quickly review what it means. On the left-hand side of this slide, you see a plot of gain, log of gain, as a function of bias voltage on avalanche photodiode. When the bias voltage is small, the gain is equal to 1, which means that there is no gain. An avalanche photodiode operates as an ordinary photodiode. When I increase the reverse voltage, a gain appears. The gain in avalanche photodiode is due to impact ionization of silicon atoms by either electrons or holes. If the voltage is below the so-called breakdown voltage, the log of gain as a function of bias voltage follows roughly a linear relationship. In this linear region, an avalanche that starts in the APD quenches or stops by itself. It's not a self-sustained. However, if the biasing voltage exceeds the breakdown voltage, the avalanche photodiode enters into Geiger mode. In this mode, once the avalanche begins, it sustains by itself, i.e., it would be in perpetuity if we did not do something to it, i.e., for example, externally bias it. SiPM microcells operate in this region with the bias voltage few volts above the breakdown voltage. The typical breakdown voltages for SiPMs range from or are on the order of few tenths of volts. Before I move on to the next slide, I would like to point out that for SiPM, the effectiveness of impact ionization is the same or approximately the same by electrons and holes. So they have almost equal probability of ionizing silicon atoms. The gain in the Geiger region can be as high as 10 to 6 and even 10 to 7 versus a few tenths in the linear region. Let us now discuss the principles of operation. This slide is quite busy, and I'm going to spend the most time on it. What I'm going to present to you, dear audience, is the basic model. More sophisticated models exist, and on the next slide, I'm going to give a good reference for a greater insight into how silicon photomultiplier operates. To explain operation of a single microcell, I'm going to use electrical model of an APD in Geiger mode. The model consists of a capacitor, a junction which represents capacitance of the depletion region. Its typical value for SiPM is on the order of 100 femtofarads. Then we have a resistor RD, which represents the resistance of the avalanche region during the avalanche, and the typical value of RD is just a few hundred ohms, so it's very small. Then we have a voltage source, VBD, and a switch. This is a light switch. The switch closes when a charge carrier injects itself into avalanche region due, for example, to a photon absorption. So this is APD. In series to APD, we have a quenching resistor, and the typical value of the quenching resistor is on the order of a few hundred kilo ohms, in fact, even up to mega ohms in some designs. Above our electrical signal circuit, we have IV plot for the potential. So on the x-axis, we plot the potential at this point, so between the RQ and CJ, and the current will be the current that is shown in red. This current will be internal current to SiPM, which we users cannot observe. The current that we can observe will be the blue current, which is shown on the graph on the upper right corner of the slide. When SiPM pixel is in the ready state, the potential on the junction capacitance with respect to the ground is equal to V bias. Please note that V bias must be larger than breakdown voltage by a few volts, 1, 2, 3, 4 or so volts. Because the switch is open, this potential is here, V bias, and thus the voltage across RQ is equal to 0. No current flows through RQ, and there is no red current, no internal current as well. On IV characteristic, we are at this point. A photon comes in. It creates electron-hole pair. One of the carriers is injected now into the avalanche region, and let's suppose that avalanche initiates. At the instant the avalanche initiates, the switch S closes, and thus, almost instantaneously, the junction capacitance tries to discharge itself through the circuit on the left or through RD. On IV characteristic here, above, what happens is that we suddenly go from this point on the x-axis to the on state, and the current shows up. Initially, that current has a maximum value, and then it declines with time. And so this current I'm now pointing is the red current. Because of the red current, potential at this point decreases, and thus a voltage appears above across RQ, and thus blue current begins to flow. Thus, at the very beginning of the discharge, the user is going to see a current pulse forming, starting at 0 and then rising higher and higher and higher and higher until the following happens. So the red current diminishes, the voltage here diminishes and approaches the breakdown voltage. When the voltage is close to breakdown voltage, there is not enough electric field strength in the avalanche region, and eventually the avalanche is quenched. The red current drops to 0, and our blue current reached the maximum value I max. At that instant, the switch opens, red current becomes 0, but the blue current persists because it is now recharging the junction capacitance back to the bias voltage. Looking at the current pulse that we obtained from the microcell, we see that the leading edge is not the same as the lagging edge. The time characteristics are different. So here the time constant for the leading edge is given by RD times Cj, and this combination typically is equal to 1 to 2, 3 or so few nanoseconds. So it's very fast. The rise time is very short. The fall time, however, has a time characteristic of RQ times Cj, which is typically on the order of tens of nanoseconds. This phase, from the moment when the avalanche was quenched, is known as the recharge or recovery phase. And it takes about 5 times constants for the microcell to fully recover, i.e. for the voltage at this point to become, again, equal to V bias. The gain is equal to area under the curve. This is current versus time. And so the area under the curve is going to give us the amount of charge that was produced as a result of single carrier injection. After some mathematics, one finds that the gain is given by delta V, or V bias minus breakdown voltage. That delta V is known as overvoltage, which is one of the most important parameters affecting operation of SiPM, times junction capacitance. And to have dimensionless gain, we divide that by the fundamental charge, E. What I find surprising is that the gain is independent of the quenching resistance. However, the value of quenching resistor is very important. If the value is too low, it is possible that the microcell would not be able to quench itself. So care has to be taken into choosing the correct value, and the choice here will be done by a manufacturer of the correct value of RQ, not the user. We don't have control over that. The waveform that I just described, we're going to refer to as 1PE waveform. However, when one actually observes a 1PE waveform with a very fast oscilloscope, i.e. having a great deal of bandwidth, one may sometimes observe another component, we refer to it as fast component, on top of the slow component, and is the slow component I just described on the previous slide. This fast component may be due to parasitic capacitance across RQ. What I discussed so far is the very fundamental operation of a single microcell. A more detailed analysis is necessary to accurately describe 1P waveform, and I highly recommend an excellent, very readable paper by Marano et al. 2014. I predict that this paper will become a standard in the future for describing operation of SiPM. So we've discussed operation of a single microcell, but SiPM has many microcells, thousands as a matter of fact. And so what about if several microcells go off simultaneously or at different times? What is the output? The output will be chronological superposition of 1PE waveforms. Before we move on to other topics, I would like to raise a few key points about operation of a microcell. First of all, there is no dead time. Sometimes one hears in connection to SiPMs this term of dead time, meaning that during recovery, the microcell is insensitive to light. This is not so. During recovery, microcell is still sensitive to light, though with lower probability. As the overvoltage, or as the voltage on the capacitor increases, the probability of additional avalanche increases. So there is no such a thing as dead time. Although there is a fast component in possible existence of fast component, the presence of the fast component does not make SiPM faster. Again, a microcell still needs a full recovery time, in fact 5 times the time constant to fully recharge itself to the on state. So fast component does not make SiPM faster. When one makes a more detailed analysis of operation, one finds that the recovery time is affected by external or front-end electronics. Again, I'd like to make a point that without front-end electronics, a photodetector is useless. Therefore, our photodetector has to interact or does interact with front-end electronics. If I use a load resistor to convert current to voltage as often as desired, our recovery time is going to pick another term proportional to number of microcells, junction capacitance, and the load resistance. So higher these numbers are, slower SiPM becomes. Let's now spend some time discussing some key optoelectronic characteristics of SiPM. In particular, I'm going to discuss photon detection efficiency, some more comments on gain, then we'll discuss noise, the 3 types of noise that exist in SiPM. We'll spend some time discussing dynamic range and linearity. These 2 concepts are closely linked together, and time jitter. Photon detection efficiency is the probability of photon detection. It's given by a product of 3 factors. Geometrical fill factor, which we discussed previously, quantum efficiency, and probability of avalanche. Simply speaking, for a photon to be detected, it has to first strike the part of a microcell which is actually sensitive to light. That's why it is dependent. Then a photon must penetrate into the silicon structure. It has to be absorbed. It has to create electron-hole pair, and one of those carriers must enter the avalanche region. And so that's described by quantum efficiency. Once in the avalanche region, there is no guarantee that avalanche will be triggered, and thus the dependence on avalanche probability. The fill factor is only weakly dependent on overvoltage. Quantum efficiency is a function of wavelength, and avalanche probability is a function of overvoltage. Thus, we expect that photon detection efficiency will be a function of wavelength and overvoltage and fill factor. And this is indeed what we see. On the left-hand side, in the top left corner, we see a plot of photon detection efficiency as a function of wavelength. On the red side, the PDE is limited by response of silicon. Let me make a note that currently all SiPMs are made of silicon. This is likely to change in the future. So silicon cannot absorb photons above about 1100 nanometers. On the blue side, we are limited by the transmission of the silicon oxide. Thus, for a typical SiPM, PDE is going to have maximum somewhere around 400, 500 nanometers. The plot from Otto et al. 2016 shows PDEs from 3 different vendors for 3 different SiPMs. And one can make a note here that not all SiPMs are created the same. You can see quite a great variation in the photon detection efficiency. The peak efficiency on this plot is above 50%. Below we see a plot of photon detection efficiency as a function of bias voltage and thus, by extension, overvoltage for different wavelengths. And what we observe is that PDE increases with overvoltage but eventually flattens out, and that's because avalanche probability of course, can never exceed 1. On this slide, we see a variation of photon detection efficiency with fill factor. So it's a plot of PD as a function of overvoltage for different pixel or microcell sizes. On left-hand side, on right-hand side, we see that larger the microcell size, larger the fill factor. Thus, for a given overvoltage, larger microcell size is going to give us larger photon detection efficiency. Gain, as we discussed before, gain is equal to overvoltage times junction capacitance divided by E. Here we see a plot of gain as a function of overvoltage, and as expected, we see a linear dependence with overvoltage. For a given overvoltage, we see an increase in gain with increased size. Junction capacitance is linearly proportional to the microcell size. In the introduction to this webinar, we said that SiPM can detect such low light levels because of its internal gain. Gain is a good thing. However, good things always come at a price. The price is that the gain introduces additional noise, multiplication noise. One can think of this noise as a noise associated with the variation of the gain. It's often represented by excess noise or excess noise figure. On the right-hand side, we see the plot of excess noise as a function of overvoltage. And we see that for a total overvoltage of 2 or 3 or so volts, the excess noise is below 1.5. And this is good. This excess noise comparable, if not even lower than we have in a PNP. The factor of this excess noise is crosstalk. The type of noise, the noise discussed short in the presentation. Even though gain does not have explicit dependence on temperature, there is an implicit dependence, and that's because breakdown voltage is rather a sensitive function of temperature. Thus, if I fix the bias voltage or reverse voltage, and I vary the temperature as shown on the plot, the gain is going to change. In many applications, we desire that the gain is constant. What can one do? There are two solutions. One is to keep temperature constant, and this is probably ideal, and lower the temperature incidentally better it is because of the lower dark noise, which we'll discuss shortly. However, this sometimes may be impractical. So the next best thing one can do is to ensure that overvoltage is the same. If overvoltage is fixed, therefore gain is going to be fixed no matter what the temperature. Some manufacturers offer power supplies that have a temperature feedback or temperature compensation circuitry. Why did I say that this is next to ideal? If the overvoltage is fixed, indeed the gain is constant, but not dark current rate. If temperature increases, the dark current is going to increase. Of course, if temperature goes down, dark current goes down, and that's always good. So we do not have control, in this case, over the dark count noise. And speaking about dark count noise, every photodetector, even in absence of light, is going to produce output pulses or output current, and we refer to this as dark current. In case of SiPM, we use the term dark counts. In SiPM, there are two reasons or two origins of dark counts. One is band-to-band thermal excitation, and the second one is band-to-band tunneling. The first process is very sensitive to temperature, and the second process is very sensitive to voltage. Thus, we expect that dark counts in SiPMs will show dependence with overvoltage and with temperature. And this is indeed the case, as exemplified by the two plots at the top of this slide. The one on the left shows the dark count rate, and please note this is a logarithmic scale on the y-axis. increases with overvoltage. The constant slope here implies some power law dependence. For a typical overvoltage of, let's say, 2-3, we see that dart count rate for these SiPMs can be on the order of even million of counts per second. On the right-hand side, we see a dart count rate density in kilohertz per millimeter squared as a function of normalized overvoltage. For a given overvoltage, we see that the rate changes with temperature. In fact, the rate doubles every 5 or up to 7 degrees or so. I would like to make a note that a dark count pulse is indistinguishable from that resulting from absorption of a photon. So one PE waveform due to dark electron or dark hole looks exactly the same as one PE waveform due to absorption of photon. In summary, I would like to state that indeed the dark counts for SiPMs are rather large compared to PMTs. However, a better manufacturing, better or more pristine semiconductors have reduced these rates and are likely to reduce the rates further in the future. SiPM has two additional noises. One is known as afterpulsing. First, let's look at visually at this noise. On the left-hand side, in the upper left corner, we see a oscilloscope screenshot of output signals coming from SiPM. We see one PE waveform, we see a 2 PE waveform, but at later time, we see additional, in fact, a forest of waveforms. These waveforms at later time are afterpulses. An afterpulse results when a recovering microcell releases charge that was trapped during the discharge. That released charge can re-trigger the microcell. As we said earlier in the presentation, there is no such a thing as dead time. If there were, there would be no afterpulses. So release of that charge can re-trigger an avalanche. So a firing microcell can fire at least one more time, perhaps even more time. You could have afterpulse after afterpulse. This type of noise was quite large for earlier SiPMs. In fact, the plot that you see is probably, I would say, 5 to 6 years old. A newer SiPM shows almost no afterpulsing. Indeed, that is underscored by the plot, which shows probability of afterpulsing as a function of overvoltage. And we see that for, again, typical values of overvoltages, the probability of afterpulsing is less than 1%. It's so small that one could safely say that afterpulsing has been reduced to irrelevance. And this has been done so by using higher quality materials with fewer defects and unwanted impurities. Another interesting type of noise in SiPM is optical crosstalk. Both figures are from Knuting et al. 2014. On the left-hand side, we see two microcells. The microcell on the left is undergoing a Geiger discharge. During the discharge, we have very hot plasma, hotter than about 1,000 degrees. And through a process of Bremsstrahlung, this plasma can release light, about 3 times 10 to the minus 5 photons per charge carrier that can create electron-hole pair in silicon. The emission of light is exemplified by an image on the right-hand side from the same plot. This is an image of a single microcell, 50 by 50 microns, where we see emission of light from the center of the microcell. Firing microcell emits light. Thus, this light can either directly initiate avalanche in neighboring pixel, as shown by process 1 or 2. So a photon simply transfers from firing microcell to a nearby microcell, or the photon could reflect from the substrate. In either case, we get so-called direct crosstalk, and the resulting pulse would be 2PE waveform. If 2 additional microcells are affected, we would get 3P waveform, and so on. Another possibility is where where photon creates electron-hole pair away from the avalanche region, but still within the drift region. So here, one of the carriers drifts into the avalanche region, creating an avalanche. And this is harder to quantify, harder to correct for delayed crosstalk. Before I move on to the next slide, I just wanted to point it out that neither crosstalk nor after pulsing shows strong dependence on temperature. This is something quite surprising. However, I also would like to point out that measuring after pulsing is quite hard versus crosstalk, where the characterization is a little bit easier. So first, let's visually observe the crosstalk. On the left-hand side, we see a plot of 1, 2, 3, so oscilloscope screenshot showing the crosstalk events. This screenshot was taken under dark conditions, which means that only dark electrons were able to initiate avalanches. There was no light, and since there was no light, we did not have a possibility of 2 or 3 or 4 PE waveforms. So all those higher PE waveforms are due to crosstalk. But again, this is older SiPM. A newer SiPM shows much more reduced amount of crosstalk. Again, which is underscored by the plot on the right-hand side showing crosstalk probability as a function of overvoltage. And we see that for typical overvoltages, the crosstalk is less than 10%. This improvement has been accomplished by the usage of optical trenches, which are basically optical barriers between microcells. Unfortunately, we cannot completely isolate optically a microcell from its environment. Therefore, it is not likely that optical crosstalk will ever be reduced to 0. Let's now discuss dynamic range and linearity. This is a rather complex topic when it comes to SiPMs, and we'll discuss it in 3 regimes. The first regime is the delta illumination. The pulse of light illuminating SiPM has a much shorter duration than recovery time. On the left-hand side, we see a plot of number of fired pixels or microcells as a function of number of potentially detectable photons. The ideal behavior is shown with a dashed line. The study by Grodzicka et al. Used 2 SiPMs with different number of microcells. And we see that in this case that higher number of microcells gives better linearity and dynamic range. Therefore, in this regime, delta illumination linearity is affected by a number of microcells. A larger number, higher the linearity and dynamic range. It is also true that the linearity and dynamic range is affected by crosstalk and after pulsing as well, but not by recovery time. The same study now investigated situations where we have now illuminating pulses of different durations from 9 nanoseconds to 850 nanoseconds, but containing the same number of photons. So the number of photons is fixed. What we vary is the duration. Again, the dashed line, which is difficult to see here, diagonal, shows the ideal behavior. Looking at the plot, we see that as the duration of the pulse increases, linearity improves. For 850 nanoseconds duration, we are very close to almost ideal behavior. In this regime, the linearity and dynamic range are affected by recovery time, in addition to number of microcells and the duration of illuminating light pulse. The third regime which still requires further investigation, is one where the duration is very high, on the order of hundreds of microseconds, as shown by the plots on the left-hand side from Vinogradov et al. The study illuminates SiPM with a light pulse of duration 150 microseconds. The red line here is the response of SiPM. Now please note the fidelity. The output of SiPM approximately outlines the shape of the light signal. There is some transient component, quite weak. However, if I increase the amount of impinging light, please note that the fidelity is greatly jeopardized. There is a rather strong transient component. The study notes that this regime requires further analysis, further consideration. And unlike the previous two cases, there is no yet simple analogical formula or understanding of this regime. Let us now discuss time resolution or jitter. Time resolution is a measure of variation in transit times. We often represent this variation using plots as shown. These are known as single photon plots. This allows comparison, easy comparison across different studies. From the plot, we see that the single photon time resolution is a function of overvoltage, regardless of the microcell size, whether it's 25 or 100. There is a decrease in the jitter. Around typical overvoltages, 2 or so volts, the jitter is on the order of about 180, 100 picoseconds. This is very good. This is comparable to what one gets from a PMT. So in summary, I could say that SiPMs have in fact excellent time characteristic. Let us now discuss modes of operation. There are three basic modes of operation. One is photon counting. One would use this mode if one can distinguish individual pulses due to photons. So this mode refers or corresponds to low light level illumination. However, as the light level increases, at some point we will no longer be able to distinguish individual pulses. Can SiPM be used in such situations? And contrary to mischaracterization in the past, the answer is resounding yes. One can use SiPM also in analog mode where we do not count individual photons. It's perfectly okay, just like photodiode or PMT. The third mode, which I'm not going to discuss much in this presentation due to shortness of time, is scintillation counting, where one integrates the output signal due to a bunch of photons that were produced due to some incoming ionization energy. Whatever mode one uses in conjunction to SiPM, one must absolutely have front-end electronics. Again, without it, any photodetector is useless. The type of front electronics that one can use with SiPM will depend on a specific application. Each one has pros and cons. I'm just going to list them as a reminder, and thus one can use, for example, charge-sensitive amplifier or transimpedance amplifier. The virtue of this one is that we have a virtual ground, which means we are not loading SiPM. One can use a voltage amplifier. Here, a current pulse is converted to a voltage signal, which is then further amplified. As mentioned before, SiPM is a current source, but it's a rather strange current source. A An ideal current source is one that has infinite output impedance. In case of a SiPM, the output impedance has a rather small resistive part, and that's because all the RQs, all the quenching resistors, are connected in parallel. So the resistive contribution to output impedance is very small. On the other hand, the capacitive contribution is quite large because all those CJs, junction capacitances, are connected in parallel. Thus, if one loads a SiPM with a resistor, as we discussed before, one is going to increase recovery time, which means one is going to slow down the device. Therefore, it's highly advisable to use current buffers. The current buffer here is basically impedance transformer. In ideal current buffer, this RS would be equal to 0, and the current here, IS, would be converted to a current I out with perhaps the same value, but with very, very high output impedance. And then one can connect a desired additional front-end electronics. Moving on to the next slide, I just want to make a comment that this single slide might deserve an entire webinar, or better yet, even a single circuit could use one webinar. These topics are quite complex and pose the major difficulty in setting up scientific experiments. So let's briefly remind ourselves the basic idea of digital photon counting. So here, the current pulses are detected with some preamplifier. The amplifier, then we are going to apply discriminator, either lower level and upper level, or a combination of these to discriminate against unwanted pulses. Then we're going to shape the pulse so that it can be counted with a digital counter. Here, the result is number of events per second, not voltage, not current, but number. In a typical photon counting event, one first would count events due to dark events, dark current, then with light, and by appropriate subtraction, one will get the correct or appropriate rate. The idea in analog is that, again, we cannot distinguish individual pulses. Thus, we can measure a time average. This could be either current, if we use ammeter, or voltmeter, of course, after appropriate amplification. Here, this time average is going to be proportional to the input light level. Therefore, in some sense, this is also photon counting. We can deduce how much light was impinging on the SiPM. Let's again look at modes of operation. This is a plot of detected photons versus number of incident photons, and we see that there is some overlap between the two modes. Minimum detection limit is the lowest light level that one can detect with SiPM. And what this chart says to us is that we can lower MDL, which is desirable, by doing two things. One is to cool SiPM. By cooling SiPM, we are lowering the dark count rate. And the second thing one can do is to limit the bandwidth. In this presentation, one can be confused by now. We said this depends on that depends on this. So what is, for example, the appropriate setting of the overvoltage? And the answer may be the appropriate value of the voltage is one that optimizes a signal-to-noise ratio. On the left-hand side, we see a plot of signal-to-noise ratio as a function of overvoltage for different values of light level. We see that higher the light level gives higher signal-to-noise. It's always true. More light, better it is. But suppose I concentrate on a single light level, maybe shown in green, 2 picowatts. And so we see here that when I increase the overvoltage from 2 further on, the signal-to-noise increases, which means that overvoltage of 2 would not be ideal. The reason why signal-to-noise increases is because we get more gain. We also increase photon detection efficiency. However, As we increase the overvoltage, eventually signal to noise maxes out or plateaus and then declines. Having higher overvoltage here would not be beneficial because signal to noise declines. It declines because higher overvoltage creates more noise. Crosstalk and dark counts depend more steeply on overvoltage. So they have more than a linear dependence. Please note that the appropriate overvoltage for these different light levels decreases as the light level decreases. So for 0.2 picowatts, the overvoltage, appropriate overvoltage will be about 434, whereas for highest light level, probably around 5 or so. Let's now briefly discuss applications where SiPMs are already being used and two others where they may be used in the future. One great success story of SiPMs is time-of-flight positron emission tomography. This is the medical technique of imaging processes, physiological processes in organs such as brains or liver. Some challenges of this application are as follows. We would like to have very good temporal resolution. I would like to have spatial resolution, and we are going to deal with weak signals. These challenges pose challenges onto SiPMs, onto detectors. Going to the right-hand side, we see all green, seeing that SiPM satisfies these challenges. They are fast detectors with minimum jitter. They have small active area, which is one situation where actually small active area is good, not the hindrance. And they are sensitive because of their high internal gain to weak signals. There's a great deal of transitioning now taking place where users are replacing or exchanging PMTs for SiPMs. It's likely that the transition will be complete. Another interesting application is LiDAR. This is a technique to measure distances to objects using light. And the focus of this slide is LiDAR in conjunction to self-driving cars. Thus, some challenges are a device must be able to operate in ambient light. And SiPMs are immune to straight light. You cannot destroy SiPM by exposing it to full light as something that you could do to a PMT. We have to be able to detect a range of distances, and we need eye safety, which means the light that we're going to work with must be in infrared. And here it's not green, it's yellow, not red, but yellow. It will be good to have higher sensitivity in the red part. Please note that the SiPMs I discussed do have sensitivity in 900, around 900 level, but it would be good to have more. It's likely that in the future other semiconductors will be used to achieve that higher sensitivity. Another green is power size, power consumption size, sturdiness, all green for SiPM. Another application where perhaps in the future SiPMs will be used is flow cytometry. This is a technique, optical technique to interrogate cells, biological cells. And so some challenges are we can deal with the weak fluorescent light. And so here it's green for SiPM. It's a sensitive device. However, we can get varying light levels from very weak to quite strong, and the dynamic range of SiPM, admittedly, is not as good as that, for example, for PMT. Another, sometimes we use dyes that are going to emit in infrared, and again, the same hindrance as before. It would be good to have higher sensitivity in near infrared. We almost reached the end of the webinar. I would like to summarize, conclude, and also briefly discuss some trade-offs associated with SiPM. SiPM is effectively a photocurrent source, and the resistive contribution to the output impedance is low and the capacitive contribution is high. And this poses challenges to front-end electronics. The second point, there is no dead time. We talked enough about that. A pixel or microcell has sensitivity during the recovery period. Operation of a silicon photomultiplier is affected by three external factors, primarily overvoltage, temperature, and front-end electronics. Every photodetector is going to communicate, is going to interact with front-end electronics. Then we have some trade-offs. There's a gain versus speed trade-off. For a given overvoltage, the gain increases with Cj, but larger Cj increases recovery time, all else being equal. Sensitivity or PD, noise trade-off. Increasing overvoltage increases PDE at a price of higher dark count rate, crosstalk, and after pulsing. Gain, noise trade-off. Gain increases linearly with overvoltage. However, dark counts and correlated noise increase more steeply with overvoltage. Linearity dynamic range versus speed trade-off. Linearity and dynamic range improve as the number of microcells increases. However, if a load resistor is used to convert current to voltage, the recovery time has an additive component which is proportional to total number of microcells. So sometimes it may not be advantageous to get SiPM with tens and tens of thousands of microcells because of this penalty. The temperature compensation circuit stabilizes the gain, but the dark count rate will change with temperature. The optimal setting over voltage is one for which signal to noise is maximum. And this signal to noise is the signal to noise that I get at the end of the front end electronics. It's the final one that I would tabulate in my lab book. Using manufacturers' data sheets for comparing SiPMs from different vendors is not optimal. The better approach, if available, is to rely on peer-reviewed academic side-by-side and objective comparisons. The data sheets often report measurements at various conditions, and so it's very hard to directly compare. Direct comparison requires exactly the same conditions, and this is a standard procedure in academic research. Selecting and optimizing silicon photomultiplier for a given application may be a complex process, and contacting the manufacturer can save a great deal of time, effort, and money. I would like to thank everyone for listening to this seminar. I would like to leave you with a little bit of PR about my previous webinar and upcoming presentations, and at the bottom, the contact information. Again, thank you very much. I greatly appreciate your time.
Thank you. Thank you very much, Slawomir. And if you have any additional questions for Slawomir, now is the time to enter them in the question box. Slawomir, we do have a few questions here that I wanted to ask you. First question is, are there characteristic and performance differences between SiPMs from different manufacturers?
Yes, the answer is yes, as we were able to see some slides ago where I showed photo detection efficiencies from different vendors. There were substantial differences. Likewise, one would see such differences in plots of dark currents and other characteristics. I like to compare SiPMs to cars. So there is the idea of a car, but different companies, different vendors, of course, offer cars with different properties. So we have a concept of SiPM, it's a photodetector, but how exactly it operates, what are its exact characteristics will vary from vendor to vendor, especially dependent on the structure, which is usually a trade secret, and purity of the materials used. But purity will often mean, higher purity will often mean higher cost.
Okay, thank you. Next question. I've heard dead time being mentioned when discussing SiPMs with others. Could you clarify?
Yes, I am on a mission to eliminate this phrase when talking about SiPMs. There is no such a thing as dead time. Again, a microcell, once it begins the process of recovery, the probability of avalanche increases with time. It's not maximum, but it's not zero. And thus, a recovering microcell can recharge. Again, if dead time were real, we would never have after pulsing.
Thank you. Next question. I heard from other manufacturers that temperature compensation and temperature stabilization are not necessary. Is this correct?
This is not correct. The breakdown voltage is a very sensitive function of temperature. Without temperature compensation or cooling, as ambient temperature changes, the breakdown voltage changes. For fixed bias voltage, thus over voltage is going to change. When over voltage changes, gain will change, and other characteristics like PDE, in fact, all other characteristics are going to change because almost everything in SiPM depends on the over voltage.
Okay, thank you. And our last question here is, can SiPMs replace PMTs in all applications?
Not likely. Remembering the very first slide where I justified why SiPM is an exciting device, we saw that the depth or the lowest levels that SiPM can detect are not as low as those for PMT. So when we are dealing with photon fluxes of few tenths per milliliter square per second, PMT is still the only photodetector capable of detection. And thus there are some applications like bio or chemoluminescence where we're dealing with diffuse light of very low level. PMTs still hold a great advantage over SiPMs. And so I think my webinar was not really to convey the idea that SiPMs are kicking out PMTs. No, it's another choice. And there will be some applications where SiPM is going to do much better, like PET, positron emission tomography. There, the replacement was completely justified because SiPM has clear advantages. But there will be applications where SiPM will not have clear advantages. So I do not foresee the end of PMTs. After all, PMTs are great devices and work excellently in certain regimes.
Okay, thank you very much, Slawomir.
Thank you.
At this time, I will close the webinar, and I just want to mention that if you miss any part of today's presentation or want to share it with coworkers and colleagues, you can find the video later today at photonics.com/webinars. Once again, thank you for attending today's webinar, presented by Hamamatsu Corporation and hosted by Photonics Media.